In this video, we're going to go over a special type of solution called a buffer. We're going to go over what a buffer is, how a buffer actually works, how to figure out the pH of a buffer, how to prepare a buffer in a laboratory setting, and we'll go over a special type of buffer that you can make in kind of a roundabout way, and I'll very briefly touch on the actual calculations of adding a little bit of acid or a little bit of base to a buffer and seeing what happens. All right, so to start off with, definition of a buffer you're probably familiar with is a solution that resists changes to pH when you add an acid or a base. Why is this important? Well, all biological systems require specific pHs for whatever reactions they need to happen to occur. Your blood, for example, has two buffers in it, a carbonate buffer and a phosphate buffer, which keep your blood at a fairly consistent pH of 7.4. If you go up or down even so much as a tenth of a pH unit, then the reactions that are supposed to happen don't happen either as efficiently or won't happen at all. Now, the way that you actually create a buffer is fairly straightforward. It involves taking a weak acid or a weak base and its conjugate substance. Right, so if I want to, for example, make a buffer with the acetate ion, I would use the weak acid, acetic acid, and I would use some form of the acetate ion, which is its conjugate base. Now, it doesn't matter what acetate I use, so long as it's soluble. So if I wanted to make my acetate buffer, I would combine acetic acid and sodium acetate. As long as both of those substances are present, you have a buffer. Right, so here's how it works. We'll take, for example, the phosphate buffer that is in your blood. The phosphate buffer is the dihydrogen phosphate ion and the hydrogen phosphate ion. But here's the magic behind a buffer, though. Let's say we want to add a strong acid, like let's say hydrochloric acid. Hydrochloric acid will react with the basic component of the buffer to produce hydrochloric acid's conjugate base, chloride, which remember, chlorides are negligibly basic, and the dihydrogen phosphate ion, which is the other component of the buffer. What I'm basically doing is I'm basically exchanging a strong acid for a weak one. Right, so weak acids have less of an effect on pH because they don't dissociate completely, and I'm exchanging the strong acid for that. Same thing with the base. Right, if I take sodium hydroxide, which is a strong base, and I add it to the acidic component of my buffer, I take a strong base and I turn it into a much weaker one. So this is ideally how a buffer works. We replace strong acids and strong bases with weaker versions of them. Now, another important thing to know about a buffer is what's called buffer capacity. Capacity is how much acid and base it can react with before you use up one of the components. Because remember, a buffer only exists as long as both components are in the solution. Once one of them is gone, the buffer is broken. So capacity tells us how much there is. This is usually measured in moles. Here's how we find the pH of a buffer. pH is it's a fairly straightforward equation. We use what's called Henderson-Hasselbalch. You'll see me refer to it as HH when I write it up because I'm lazy. Right, the Henderson-Hasselbalch equation, the pH of your buffer is equal to the pKa of your acid plus the log of the base concentration over the acid concentration. There is a shortcut we can use to this, though, right? Because buffers generally tend to take place in the same solution, the volume of the acidic portion and the basic portion are the same, so they'll cancel out, which means we can generally just use moles or, more commonly, millimoles as our base over acid value. Now, one thing to keep in mind is if you are using concentrations, take into account potential dilution. That's why we generally tend to use moles, especially when we're mixing together two different solutions, because moles just work no matter what. Preparing a buffer, so laboratory preparation for a buffer. You are going to be doing this in the classroom, so here's how this is going to work. I'm going to present you, and I'm going to say make a buffer with a pH of 6.4 and a capacity of 0.05 moles, let's say. What you would do is you'd find an acid or a base, if it's above 7, with the pKa closest to the substance's pH, right? So if I'm trying to make something at 6.4, I'd find a weak acid whose pKa is as close to 6.4 as I can manage. Then I use Henderson-Hasselbalch to figure out the ratio of base to acid. I use the buffer capacity and the ratio to tell me how many moles of each are needed. And then finally, the last thing you have to remember, whenever you're using salts, always use soluble salts, so sodium or potassium salts especially. Now, there is another type of buffer I should probably cover very briefly, and those are what I'm calling sneaky buffers. The reason why is because you don't make these through the normal portion of mixing a weak acid with its conjugate substance or conjugate base, for example. The way you actually make a sneaky buffer is you take a strong acid or strong base and you react it with excess of the weak substance you want to use, right? So it's conjugate. So let's just use an example. Let's say I wanted to make an ammonium buffer, right? So an NH4 plus buffer. What I can do is I can take 1 mole of hydrochloric acid, react it with 1.5 moles of chlorine according to the equation that I just put below. Since HCl is a limiting reactant, it's going to get entirely used up, meaning that we're not going to have any HCl left over in our final solution. That 1 mole of HCl went to produce 1 mole of ammonium. To produce that mole of NH4, I had to react 1 out of the 1.5 moles of NH3. Right? So I'm going to produce 1 mole of NH4 from this reaction. I'm going to have half a mole of NH3 left over, right, because the 1-to-1 ratio. So because I have a weak base, ammonia in this case, and its conjugate acid, the ammonium ion, I have a buffer. Right? So this buffer is present, and its buffer capacity is 0.5 moles. You will see these quite frequently, especially when we do titration curves a little bit later on. So a very important skill for you to get good at is being able to identify when you have a buffer present in a system, whether it's a traditional buffer or one of these kind of sneaky backdoor buffers. And then the last thing, I'm going to very briefly cover this, but calculating a pH change based on adding an acid or a base to a buffer, this isn't that bad. What you do is you just use stoichiometry to figure out how much of your acid and base are left over. Right? You can generally BCA tables like ICE tables, except they're going to use moles instead. These will generally be useful to help you figure that out. And then once you figure out how many moles of acid and base you have after the reaction, you can then plug it back into Henderson-Hasselbalch and get the pH of your buffer at that point. Now, the one thing I should say about this calculation is that while we will be doing this in class, especially as part of our titration curves, it is not going to be tested on the AP exam ever. That is a specific exclusion statement that they put out. I'm just having you do this because, again, first-year chemistry courses, college courses, generally require you to do this to a certain extent, so I'm going to mirror that experience and have you guys do this.